Recording has started. Yes. And then I will record here as well. Okay, good. So刚刚可以，现在就不行了，真是棒。我连线都连接了，现在还不行，不知道你在干嘛。这些都试过咯，就是我无法投影我的 iPad 到上面，而且上次好像也是这样。重来一次。暂停。好 ，OK。真的耶，上一次也是忽然就不行，而且之前还可以的时候，真的是很棒。你知道所有的 device 啊，都有差一点点的好处，就是用到最后还是就是苹果真的是比较好，可是它就会有这种无法投影的，就是有的时候不行投影，有时候可以了，奇怪。好，那我们就继续下去了。Okay, so yes, let's continue our lecture. All right. So how do you feel about last week? And I hope this course is, well, it will be difficult. It will definitely be difficult. But I will try my best to help you to understand this by speak slowly and also a better form of the PowerPoint. All right, so try my best. And last time we explained this concept. The concept is that if we want to see the force, internal force, or the stress at any point of a material, for example, here, I want to see the force or the stress at that point, I need to cut it. Okay, I cut it and separate them, and then each part must follow equilibrium status, right? So because you cut it, firstly, you don't have this arrow, right? But you have the rest of the arrow. You need to make this part equilibrium. So you need to put one force here to make it equilibrium, to make this part stay here, okay? And the upper part is still okay. Yes, you see that upper part and lower part, you made them equilibrium, and then you have two diagrams, two force diagrams. And when you put it back, okay, these two force, F max, is opposite with the same value, they will cancel each other. When they cancel each other, when you stick back to the two parts of the material become one, right? And then your internal force cannot be seen in these figures. Okay, so that's the basic concept. If you want to see the force or the stress, you just cut it, cut it, cut it. All right. So normally we will just cut one section to make everything easier. All right. So this is a really important concept for you last week. And then I talked about why stress, because it will makes the behavior of the material independent with independent to geometry, shape. Okay, so you see different shape, the same material. If you're using strain and stress, you will have one lines. If you have only material, the same material, you have the same line. Okay, this is the reason. And then we talk about the actual behavior that the true stress use actual area. So sometimes if you do the tensile, the area, cross-section area will shrink. So it will obtain more higher, greater sigma T compared to sigma E. Okay, because E always using initial area. Okay, and the true strength also, it will be difficult because you need to sum them up all the instantaneous strength, which means that the strength increase with the time. Every time step strength, you need to sum it up together. And then you've noticed that because the initial gauge length is smaller than the length at each time step. So your epsilon T is less than epsilon E. Okay, and then we review the concept. You know that you have known. You already know that, right? In the introduction of material science engineering. So I just make it quicker, and then you know the behavior of the loading and unloading, right? If you're loading before the elastic limit, it will go back to its original position of the shear strength and stress diagram, right? But once you overpass the elastic limited, when you unloading, it will follow the tangent line, really similar to the previous initial slope, and go back to the point that they are not at the origin, is somewhere here, and the strain in this distance called a residual strain, and it will increase when you start to loading again and push further to the point, and then follow the same rule. So you can see that the region is keep moving to the line here is keeping moving to the right, and you're generating more permanent strain. Okay, maybe epsilon P or maybe other symbol. All right, so this is what we learned last week. Okay, and then we talk about creep. Creep is, well, it's long-term fixation, a long-term fixed loads, and elongation increase over time. So which means that this is a kind of complicated behavior. So actually, we're not really calculating this in our midterm or practice. Okay, just give you an introduction that the creep is occurred in our materials. Okay, and creep, you can two typical creep scenario is that if you hang a bar, maybe maybe the light above you, you see the bar. I think the bar is last for more than 20 years, right? So it must be longer than 20 years ago, right? So it's even you don't have the pressure. Well, you must be have the load underneath because you have the lamps underneath, right? So the elongation firstly, once you put on the stress, put on the weight, it will elongate. For example, this is weight, okay? So once you put that, the bar elongate a bit to reach to here, and then after long time, it will go a little bit longer than that. Sorry. And then kind of saturate. All right. So it's kind of make it even you don't change the weight, it will still has a longer delta. Okay, or if you fix a wire between two walls, and you can see that the elongation won't change because you fix two ends, right? But the stress in this wire will decrease. So once you fix, I mean, you have a wire, right? It's kind of dangling there, but if you fix it to the left and fix to the right and make it a straight line, there must be some tensile stress in the wire. So at T naught, it suddenly jumped to sigma 0, and then over time, after a few years, after a few years, the stress will decrease. So which means that your wire or sometimes will become loose. Okay, loosen. Yeah, you get my idea, right? So easy. Next page will be a most important pages that you in the material science engineering, right? Which is Hooke's law. Hooke's law, I believe all of you know that even when you are senior high school student, right? Linear elasticity. The stress strain curve is elastic and linear. Oh, you notice that why I said linear. For example, this one, when the loading unloading before the elastic limit E, it is elastic, right? It is elastic because it returned to its origin, but it's not linear because this is a curve, right? But now we fix our assumption or simplify our problem. That's before that, we only talk about linear, before the elastic limit, we only talk about linear elasticity. So very simple, okay? We assume that the stress strain curve is elastic and linear. The material obeys Hooke's law, sigma equal to E times epsilon. E is Young's modulus. The Young's modulus connecting sigma and epsilon, okay? Yeah, so you can see that epsilon has no unit. E must be the same unit, right? So the E must be unit with the par or Newton per meter square. All right, so the slope of this linear elastic region is Young's modulus. You see elasticity here, but not linear elasticity. So this is not linear, okay? This is linear. This is not linear, okay? Although they are all elasticity, they can all come back, return to its origin. It's okay, but it's not suitable for Hooke's law. But you know that this is too difficult, okay? So we only focus on this one in our course, right? Next one, next page is Poisson ratio. Poisson ratio. The Poisson ratio is that when an object is subjected to an axial tensile force, all right, it elongates in the axial direction and lateral contraction occurs. Well, it makes sense, right? You have a bar, maybe, okay? And then if you have an axial force, okay, axial force, all right? And then your lateral means the direction perpendicular to your axial force, okay? Your lateral must be contract, okay? Makes sense, right? So the ratio between the two strengths axial strength and lateral strength, their ratio is Poisson ratio. Okay, the Poisson ratio. And you notice that there is a minus sign on it, right? Minus. The reason why is that because if your axial force is positive, it makes positive strain, but you will always make the opposite side of the strain, lateral strain, it will shortening, right? So when you have a positive here, you must have the minus lateral strain. But vice versa, if you have a positive lateral strain, you must be compressing it, right? So to make this value positive, you add in one minus side, so you can make this positive. The value, Poisson ratio become a positive value. Okay, so lateral strain, we give you the plan on it. The epsilon, well, it's epsilon, right? So what you learned that in the previous few pages is epsilon. So that's the ratio. And well, we can say this is nu. Okay, we can give you a nu. How to pronounce it? Nu. Okay, Poisson ratio nu equal to minus epsilon 1 over epsilon. Okay, so typical material. The nu become in the between 0.25, 0.35, more or less most of the material. But some very interesting material like rubber is 0.5. Okay, and we said the theoretical maxima value is 0.5. Oh, why? Well, later we will explain to you. All right, why this 0.5 Poisson ratio is theoretical maximum. I will explain to you in the future. Okay, so just give you a concept for that. I believe you understand Poisson ratio now. So yeah, that's it. So basic introduction is almost finished, but one last page is waiting for us. Again, I'm going to tell you this course is not difficult because we have many limitations. When you finish this course, well, still a lot of mechanics problem we cannot solve, okay? Because we have too many limitation in this course. Material mentioned in this course are linear elastic. So a lot of material is not linear elastic. We cannot predict their behavior. And this is a homogeneous material. Oh my God, we have many things, many materials are inhomogeneous. So, and also isotropic. Wow, this kind of limitation plus limitation plus limitation. So basically what we learned that is really introductory course. All right. Then another supplement, well, or extra information for you is that what is orthotropic? Orthotropic means, well, material property is differ in 3 perpendicular direction. So definitely not isotropic, right? So as you can see, this material is a typical material that has orthotropic material behavior. You can see that they have their material is symmetry in 3 planes, which is perpendicular to each other. You can see that the material with this plane, you see symmetry, and here symmetry, and also here, if you cut through the plane, you can see that before in front of the plane, cutting plane, and behind the cutting plane, they are all symmetry. So the material property is symmetry along perpendicular to that 3 time plans. Right. Okay, that's it. I hope you can understand what I'm talking about. If you really don't understand what I'm talking about, you can see OCW in Chinese. But well, the same, I guess. All right. So, because we now have the Young's modulus and also the information about the Hooke's law, right? So now sigma and epsilon are connected. All right. So let's take a look. There is another tube, okay, and the tube has the cap, blue cap. But now we are not considering the blue cap. We're considering the gray materials, gray tube. Okay, so the L is 102, D2 is 150, D1 blah blah blah. P is 620. E of this material. E of this material is 200 gigapar, and the Poisson ratio of this gray material is 0.3. So it wants us to calculate shortening delta, the displacement delta, and lateral strand. Oh, lateral strand. And delta D2, delta D1, the increase in the diameter, or delta T, oh, the thickness change. Okay, so let's take a look. So now sigma equal to E times epsilon. That's what we learned of the Hooke's law, right? So now, how can we get this? We don't have sigma, we don't have epsilon, we only have E in our problem, right? So we need to connect them to our definition. The epsilon equal to delta divided by L. And sigma equal to P divided by A. So once we write down here, I believe you know how to do that, right? Pi divided by 4, D2, D1 square equal to pi 4, 152, well, square, 110 square equal 1,816 times 10 to minus 6 m square. Sigma equal to minus 62,000,62,1234, because it's K Newton, right? And 1,868 times 10 to minus 6 equal to minus 7. Oh, you can see there's minus 62 because it's compression, right? Minus 75.9 m pop. All right, that's sigma. How about epsilon? 5 minus 5.6 divided by Young's modulus. 200. E par. G means 10 to 9. Okay, 10 to 9. Again, minus 379.5 times 10 to minus 5. Okay, so this is epsilon. So if we have epsilon, we can have delta, right? Epsilon times L. Minus 379.5 times 10 to the minus 6 times 102 minus 38.709 millimeter. Great, that's it. So by using the Hooke's law and combine the knowledge we learned in the previous week, okay, we can obtain this minus 38.709 millimeter. Right. How about our second problem? You know, the best thing of the digital blackboard is that I can freely adjust what I wrote. Okay, and also we don't have the dust when you write out on the blackboard. I really like this digital blackboard, and also you can record everything, even zoom in. Wow, so I think I will never use blackboard anymore. I haven't used blackboard for 15, sorry, no, 10 years. 10 years. I only used blackboard in the first year of my professorship. Anyway, and then COVID hit, right? COVID pandemic, and then I kind of starting to study how to recording all my stuff like this. So it's quite fun. I quite like to play with all these tools. I hope it works and then help you to understand better. All right. Next, second problem. Lateral strand. Lateral strand is epsilon plumb, right? What kind of things connecting epsilon plumb to epsilon? Of course, it is Poisson ratio with the minus sign, okay? Don't forget this minus sign. So epsilon plumb equal to 0.3 minus, okay, times minus 379.5 times 10 to minus 6. You need to be really, really careful, okay? How about I change the color of this? How about I change this minus sign? Okay, don't forget this, because the epsilon here should have the positive or negative, all right? Otherwise, if you forget this and you put the minus sign here, you will make this negative. So the direction may be opposite, right? So be careful. So now you see that the lateral strain is positive. So which means that the lateral strain is positive, is increase their lateral length. Okay, I believe you can understand this. It's not difficult here. All right, the next one, delta D2 and delta D1 increase in the diameter. All right, so delta D2. Let's take a look. Delta D2 is the displacement or length change of the diameter. So you can just times the epsilon 1 times D2 original length, right? You can obtain the delta D2. All right, so times 150. So you got 0.0171 millimeter. Okay, delta D1 is follows the same concept, 113.9 times 10 to minus 6 times 110. It becomes 0.0125 millimeter. So again, the epsilon is the ratio, right? The change in the length change ratio. So all you need to do is just times this original shape, original length. You can get the change of the shape, change of the length, sorry, change of the length. Easy, right? Next is also fun. Next one is delta T. Delta T in the wall thickness. Okay, solution one. Well, I believe you know that. Delta T means delta D2 minus delta D1. Oh, is that correct? No, let's take a look, because we need to have divide by 2. Why? Let's take a look, okay? Because this is the cross section, okay? The other inner diameter. All right, and then your diameter is this, right? Outer diameter and inner diameter. So if you divide your outer diameter minus inner diameter, you have two thickness. Okay, be careful. So actually, when you do delta D2 minus delta D1, you have two thickness considered. You need to divide by 2. Okay, so this is, you need to be really careful about this. Equal to 0.0023 millimeter. All right, this is solution 1. Solution 1. How about solution 2? Solution 2 here. Okay, solution 2 is more straightforward. Okay, more straightforward. Delta T equal to epsilon prime T. Wow, sorry, I shouldn't write down different form of it. Okay, equal to 113.9 times 10 to minus 6 and times T 150 minus 110 divided by 2. All right, you got exactly the same value. All right, so again, because the epsilon plot strength is a ratio, length change ratio. So as long as you times the length, original length, it will give you the displacement change of that length. Okay? I believe you can understand this, right? This is not difficult. Then next page is the first difficult part in this course. Next page is the first difficult part in this course. It's called shear. Okay, your seniors always think about why this definition. This is a little bit difficult. So yeah, the next page you need to be pay more attention about this.我看一下我手机还在录吗？哎，有哎，对。哎，嗯，对，就这样。好，大家都抄完了吗？哎，抄完了，大家抄的好快。好，那我们就继续下去喽。下一页是最难的哦。不是最难，不好意思，第一个难题哦，第一个难关哦，叫做 shear 剪切。Let's take a look. Shearing, all right, shearing. So I give you an example. Next one, you can see that there is a Y shape stuff, okay, and there's a plate, gray plate, okay, and then in the middle, in between, they connected with a bolt, 螺丝, okay. Of course, you can know that there are two holes in Y shape, two holes, and one hole in gray plates, right? Okay, so now let's take a look how these two materials apply shear force and shear stress to the bolt. So we are considering shearing in the bolt. 我们是要考虑的是 螺丝里面的剪切，不是在考虑这些蓝色跟灰色的哦，我在考虑螺丝上。Okay, we are considering the stress, shear stress at that bolt. Okay, so now the system shown below is subject to force P. The bolt is under shearing. You see, the bolt main character is bolt, not the blue white shape and the gray material. Not that. We are considering the bolt. All right. Right. So average bearing stress of area AB is sigma B equal to FBAB, where AB is projection area of the region 2. What does that mean? Let's take a look. Please, please follow what I'm. Yeah, just please follow me. Okay. So you can see that this figure has PP to do a tensile, right? So if you see from this angle, you will see this view, right? And you can see that this bolt, if we take here, you will find that this P here is going to will drag the material here go to the right hand side, right? So what thing stop it? Blue bolt, right? And this gray material trying to go to the left, what kind of stuff stop it? Blue, right? So you can imagine that the bearing means stop it. Okay, bearing in Chinese 承载、负载 ，OK， 它承载这个力量，它把它挡下来了，它把它挡下来了 ，OK。So you can imagine that the white shape is going to the right, gray material going to the left. What kind of stuff stop it? The dark blue bolt, okay. And you can imagine that this P going to the right, so it apply this force 1 on the bolt, force 3 on the bolt, but the gray part apply force 2, number 2 to the bolt. And you notice that 1 and 3 to the right, 2 to the left. All right. So the average bearing stress of area AB for the region 2 is that the bearing stress for the region 2, the bearing stress is this force divided by the area it act on it. Okay, so this is the projection. So I will tell you in the textbook, I don't think the author draw a good plot. Okay, this is really bad idea for the textbook. You see, the textbook said the AB is NMQP. No, it's not NMQP. It's not NMQP. Although the value, you see, this is the I plotted, copied from the textbook, but it's not. It should be. You should draw like this. This is the force. This is how the force flow into. Okay, the area really stop that force too. If you see in the see from here, the plot should draw like a line, right? It shouldn't be a surface that you can see. So the textbook misleading. Okay, although this is not wrong in this special case because the bolt is a circle. So even if you determine MMQP, well, they are the same. The area is the same throughout all the angle. But for the definition, you should plot like mine. You shouldn't plot like this. Do you understand what I'm talking about? Okay. Thank you. So your sigma B should be FB, well, FB, F bearing force, FB2 divided by the AB. You see, this area, or you can say this line is this line. All right? Okay? So you shouldn't draw like this. No, it should be a line. Okay? So this is the force FB2 equal to P. So we can say again, this FB2 because of due to the gray material. So issues this is P. And then if so sigma sigma B2 equal to P divided by A B2. All right, so AB2 is this one. This one. Okay. So at that part, at that region, the bolt bearing stress at that part is sigma B2 equal to P divided by AB2. So the P acting on that area, all right? Now, so the bolt has different region. So they have different region, different loading condition. So different position, they may have different bearing stress. So for the region 1 and 3, again, you see that the region 1 and 3, due to the blue parts P, so it should be half P. All right. And then, of course, that region will has sigma B1 equal to P divided by 2 over AB1. And of course, sigma B3 equal to P divided by 2 AB3. Okay? So you notice that even in the same bolt, the same material, they will have different bearing stress in different region, depending on the loading condition, load value, and the area that load acting on. All right. So I will tell you that stress is different at different point in a material. I believe actually you know this concept before, right? Because of that first important concept for the sigma mix in the handling bar, right? You can see that different stress at different point. Again, you can see different stress in different region in the same material. Okay, so I can also let you know that the bearing stress, which has a characteristic or feature that loading is perpendicular to the area. You can imagine that the area trying to stop that force, bearing that force. You can imagine that. So you can imagine this surface stopping the P here, trying to bury it. Okay, bury it. Okay, so this is bearing stress, not shearing stress. So maybe you think why you are going to talk about shearing, but why are you talking about bearing? Well, because sometimes it happens together. Okay, I will going to tell you what is the shear occurred in this example. All right, now I assume that you understand the bearing stress. Now I'm going to tell you the shear stress. Shear stress is tau, okay, tau. Well, I should write down this tau, okay? The tau here has the important feature is that loading is parallel to the area. Very important, please. You can see that this bolt not only stopped the force, also being cut like a scissor. You see, this force going to that way, and this force going to that way, and this going to that way. You can see that there must be a force here, right? Here, the force is cutting that bolt. So it's called shear. And I will continue my lecture. All right. So this is really difficult. All right. So I hope you can understand what I'm talking about here and then prepare for the next. See you later.有没有问题？有问题可以过来问我。 Okay, welcome back. All right, this is really difficult. All right, so I'm going to enter the part that the first difficult part in mechanics of material, right? So, give you a quick review that before we talk about shearing stress, we talk about bearing stress. A bearing things that it means that the area that stop the force, right? So you see that the force is going to stop by it. So you can see that is vertical, perpendicular to each other, all right? And then, sorry, I forgot to write down. I also mentioned that. The textbook has some mistake that it draw the bearing area in perpendicular to, well, it in this way is parallel to the force direction. So it's not right. It should be looks like a line in this view. Okay, and then if I draw white and white, it will corresponding to the white region here. All right, and red region here. Right, and then this red lines corresponding to this one, and the white lines corresponding to these two lines. All right, so that's how I explain the bearing stress. And then we talk about shear stress is loading parallel to the area. So you see that actually between these two forces, there must be an area that cut. The cutting plan, actually, I wanted to say that. So you can imagine that the shear force is actually occurred at that area, and that area A here has the force with the perpendicular to that area. Okay, so what is the value of that force? Again, if you want to see the force in that material, you cut it, right? So now I want to see this region. All right, this region corresponding to this region. Exactly, right? This region corresponding to this region. I hope you can see that. Okay? Have some imagination. All right? So I want to see this part. I just cut it. All right? And yeah, let's take a look. So I cut it. And I can also, because this is symmetry, all right? So I cut it here, also equal to cutting here, right? So you can see that this blue white shape, okay, blue white shape has the P here. So if you cut here, do you think this white material is staying there? Yes, they are in equilibrium state. So this two red area must give it a to the left hand side P over 2 to balance this Y shape. Okay, so you see here, this force is P over 2. All right, so that's how I get P over 2. Okay. Then, if you want to draw another things that, if you want to draw the gray stuff, the gray stuff, okay, if you cut it, your P, and you cut it, you will have P over 2, P over 2. All right. So your average shear stress is, the V here is P over 2. Okay. V is the V is shear. V is shear, right? So the V here is V equal to P over 2. Right. So P over 2 divided by A, your shear stress tau average is P over 2 divided by A. That's it. That area subjected to the shear stress, shear force, and then shear stress P over 2 divided by A was the value. Okay, the value is that. All right. I know there's still a lot of I believe you understand this, but how about other cases? So next page, I will introduce many other cases for you, and you will know more about the shear stress. All right？ 这边应该蛮难的，但还可以听得懂吧？哦，还算行吧？OK 吗？OK 吗？哎，没有人点头，糟糕了。总之，首先先讲承载力，挡住它的力，那就是会垂直于它的面积。但是在这个你会发现这个左边跟右边这样夹击的部分，你会想象一下，就是这边推这边推，它一定会有一个要把它剪开的那种力量。那剪开的那种力量就是剪力嘛，那我们就要去算算看那个剪力是多少。啊，我们不是想要看啊，当然了，剪切的力量，你可以想象一下，就是这根棒子它一个要往左边，一个要往右边这样。然后呢，所以说，我应该画不对，我应该画，不好意思，我应该把这个东西画在下面，你们会比较懂一点，这样才对。这样你应该就比较懂，好吧？这样可以吧 ？OK， 对，应该是要这样子。那这样子你就可以知道，这样比较懂。Sorry, I put the wrong position of the area. I should put here. Okay. So the area here should be here. All right. 对了，我怎么会画成这边呢？真是的，你看蓝色的下面，对，应该是这样子。Okay, so sorry for that. 然后呢，为了把它，就我要看那个地方的力量，就把它切开来。切开来以后呢，就为了要看这两个力量，把它切开来。切开来以后，P 往右走，那这两个地方就会至少是2/P。然后呢，它的2/P 就会作用在那个 area A 上面。那就是剪力作用在那个 A area 上，它就是它这一个截面的剪切应力。OK， right. So I'm sorry that I misplaced this two area. Sorry. And then next page, I will give you more cases, and then I believe you will understand more about this. All right. Next. So there are two types of shearing. The first one is direct shearing. The other is indirect shearing. Direct shearing, just like what we learned that before. Direct shearing, if you have a bar, and then if you give a force here and here, all right? And it must be trying to cut it, right? Just like Caesar. And then you see Caesar is just like this, all right? So left hand side is down, right hand side is up, all right? So if you cut it, you will see that there's a bluish surface and green surface. Well, I didn't actually break it. I just give the load. The material is at the equilibrium state. It's stable, not failure, okay? We just want to see the stress in the material. So you can see that the force here, and if I want to see the shear stress in that at that surface, we just cut it, right? And we separate them. And left hand side, I will see that surface need to be has an upward V to balance this material. Otherwise, if there's no this shear force, this blue part will go down, right? And likewise, the right hand side, you have the upper force. You need to have the shear force downward. Okay, so this V, we say this is shear force. Remember, the second concept I would like to give you, really important in this course, is that we will never say stress balance. We will say force balance. OK， 千万不要再讲说哦，应力平衡，这是错的，应力没有在平衡的 ，force 才会平衡，好吗？千万不要讲应力平衡哦。我常常应该说我在以前跟学长姐强调说，我就听在强调这件事之前，很多学长姐都会想要讲应力平衡。No， 是力量的平衡 ，force balance， 不是 stress balance。stress 没有 balance 的 ，stress 是一个结果，好吧？是一个结果。OK， so you can see shear force balanced. It makes this material not flying back. So you see that if you plot a square before the shear, if you plot a block before the shear, it is a square, all right? This is a square. Before the stress, before the shear. After the shear, you can imagine that it will look like this. Right? Because the right hand side go up and the left hand side go down. Okay? So you now know that how the shear makes the material twist. If you have a crystal or structure, maybe it's maybe it's a cube, all right? If you have a shear, it become a shape like this. 不好意思，我不会讲平行四边形。英文平行四边形怎么讲？反正它就会变正方形的话就会变平行四边形。好，如果你受到剪力的话 ，all right. So this is direct shear. And then I talk about single shear. What is single shear? If you have a material like this, and you have the force here and going to the left, I believe you know that this one is actually equal to this one. So if you turn your head to the right and you find that, oh, this brown is actually this, and this force here is here. Well, very similar, okay? It's okay. So single shear is that if you have material of brown and then you have force P to the left and force P to the right, and I want to see the shear stress, average shear stress in that area. So I just cut it, and then we leave the upper part, okay? We leave the upper part. We only see the P here. But if you have no P here, it will fly. If you have P here, and it will fly away, but it's still there, which means that the green's interface must support, give a force like right-hand side. Okay, so the right-hand side give the force P, so the green area here will give you a shear stress. So this area here, okay, and it's green. Okay, so this green area, all right, and you will have a P here. Okay, and this is A area, so tau average equal to P divided by A. Okay, so that's the situation going on here. And then I'm going to introduce double shear case. Double shear case is really similar to what the Y shape in the previous page. So you see the textbook is really, well, it's not really good designed. First example is the double shear. It makes things complicated, right? I don't know why, but anyway, so double shear is that you have the material like this, and you have right-hand side P, left-hand side P2, P over 2, and the other P over 2. All right? And maybe you think, oh, this gray thing is not similar to the previous one. No, no, no. If you draw a Y shape here, you're very similar to the previous one. Okay? So previous case is actually double shear case. So now, if we want to take a look, well, if we want to see the material shear stress at that position, I just cut it, and then we only see the right top of it, and you have P over 2. So which means that your shear also P over 2. And then we have exactly, sorry, I will copy that. And ta-da! Become P over 2, and this become P over 2. All right, so now you see that the definition is always the same. When the shear force acting on a surface, which is parallel to that surface, the surface just divided by that surface area is the shear stress at that point, at that surface. Okay, this is direct shear. The other is indirect shear. Indirect shear, oh, you can see that when before the loading, if you have the element with the square shape like this before the loading, you see that if you twist it, how to twist it? All right, twist it. If you twist it, you notice that it will mix the left-hand side up, the right-hand side down. So it will mix this square become that shape, 平行四边形. Right? So which means that even if you twist it, you will generating shear. You are generating shear stress in this material. Okay? Okay. Now, another indirect shear. What do you think? If the force, do you think your actual force P here will give shear stress? Do you think so? Do you think your P force will generating shear stress as well? Yes, it did. Let's take a look. If you draw your material with a square on it in this position, okay? Yeah, after you're loading, you will have sigma, sigma, left hand side, right hand side. Okay, so it become a elongated element. Yeah, this actual stress, normal stress. You learned that in the last week. However, if you draw your element like this, is 45-degree uplift. What do you expect it? That will change. It will change like that, right? Let's put closer look. Previously, it become like this. Okay, I think you can get it. How about this? If you draw the figure at 45-degree tilted, do you think this square become a shape like this, 平行四边形? Yes, it did. So actually, the material at that angle, 45-degree angle, also encounter the shear stress. It makes this square become this shape. Okay, so this is a really important concept. Straightforward. If you think straightforward or simply just say, oh, maybe the normal loading won't generating any shear. No, actually, in other angles, your normal stress is not normal, right? So actually, it's also generating the shear. So this is called indirect shear. OK， 啊，这边我觉得有点难。我们觉得就是，轴向的施力不会造成任何的剪力。不是哦。你可以看到这边，这是我们刚刚看到，之前看到的 case，你画的正方形正好是 xy， 正好是 xy 坐标这样子画，都对，它看不出来有任何的 shear stress，OK。但是如果你一开始画的是斜的，你如果这样拉，你会发现它其实又变成平行四边形了。那我们刚刚知道平行四边形就是知道它有 shear， 对不对？所以实际上在这个材料里面，其实材料里面你不能规定材料它一定是要让你看到是 xy 这样看到的轴是你自己定义的，所以实际上在材料的这个各个方向的角度上，它其实是有 stress 的shear stress 的分量哦。OK， 所以这是要非常小心的事情。那等一下我们就会看到。All right, so the really important concept is that even if you apply normal force, it's still generating shear stress at certain angle, which means that based on different angle, you may have shear stress component, 分量 component. All right, so that's it. So now you know this shape, square become this shape, which means that you have the shear stress element. Okay, so shear stress on an element. Previously, we just said square, but now we're going to go for 3D, become a cube. All right, so due to the balance of the force and momentums, equilibrium equations, The magnitude, blah, 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 blah. Okay, so I will going to tell you. So when a shear acting on a material, and if that material is at equilibrium state, which means that the element need to have pairwise shear. Pairwise shear. 成对出现的 shear. 成对出现的剪切. Okay? So again, let's take a look. Let's assume this cube, this element only has this tau. Is that happen? Can that happen? No, because if you only have this tau, it will fly away, right? But this element is still here. So this element need to has another shear at the opposite side to the downward to cancel this. So if you have this one, you need to have another one, another pair to cancel the upward direction force. But if you don't have these two, you only have these two, yes, you stop that at that position. But if you have this one and that one, what will it be? Rotate at the same place. This is not rotating, right? This is in equilibrium, stable state. It must has another force to make it balanced. So up and down, right and left to make it stop there. So which means that, again, concept, if you have a material subjected to the shear stress, and this material is still at equilibrium state, which means that the shear will always appear pairwisely. Okay, pairwisely, 成对出现. Okay, and this tau, again, I need to give you no, this is a shear stress. Shear stress, not shear force. Okay, if you want to get force, how can we get force? We just tau times the area of the shape. So if you want to get the surface, if you want to get the force of that surface, you just tau times the area A here. You can get the shear force at that area. All right. And then you can see that because the shear occurred pairwisely, so you see, it become a parallelopiped 还是 parallelopiped? I don't know. 平行式，平行六面体。Anyone can pronounce it? Teach me. 有人会吗？加个分好了。怎么念啊？不要查，不要查 AI，不要查。来，这怎么念 ？Parallelopiped. 对，平行六面体。没有人加分吗？没有多益900多的同学会不会？哎，我发现一件事情，就是我们就是材料系的申请学生一届比一届英文好，哎，太夸张了。每次看到申请书就多益960，950，哇930，然后怎么那么高？然后我曾经看过有一些面试的同学就说我英文很好。然后这样，英文700多，然后我想说，哎，这个也很通货膨胀。就以前我觉得，在我这个年代跟你们一样大的时候，我觉得多益700多、700、800，我觉得已经很厉害了。700多已经很厉害，我觉得啦。就现在大家都变成900多，我想说，那700多是不是表现好像没有那么好？但是在我这个年代，700多已经超强。然后没想到现在同学们的英文程度就越来越好，越来越好。我觉得你们真的是很厉害，我佩服你们。Anyway, let's go. 好的，没有人知道平行的问题怎么念吗？ 有没有要讲一下的？有人会吗？线上朋友你可以直接讲出来，没关系，就取消你的静音。对，我不会念，好，我不会念。哎，anyway，所以大家要放弃这个加分机会吗？好，没关系，那我们就开始吧。So a cube after the shear stress become parallelopiped. Yeah. Anyway, so you can see that the angle changed. The angle changed. Previously, the angle is 90 degree. Now it become 90 degree minus, well, if we say gamma, all right? If we say gamma. So for the S and Q corner, it is 90 degree minus gamma. And the other two angle become 90 degree plus gamma. Sorry, I should say pi over 2 plus minus gamma. Pi over 2 plus gamma. The reason why I use pi over 2 rather than 90 degree, because the pi over 2 is radian. Radian 进度啦啊 radian is also a ratio. Degree is human-made unit. All right, radian is more kind of ratio. Imagine that you have pi, 2 pi. So if you have 2 pi, if you have half pi, it's actually a ratio, which means that you have a circle. We only have, you only go through quarter of it. All right. So the gamma is the radian is also a ratio. So when you are talking about ratio, it can directly link to strain because strain is also a ratio. Radian has no unit. Well, units, radian is unit, but actually this is a ratio. So in physically speaking, radian is not a unit. It's unitless. All right. So we prefer to talk about radian. Okay. And minus gamma and plus gamma. The gamma here is shear strength because shear typically give you a result of changing angle. The changing angle, the angle change is in radian unit, and then you can say shear strength. OK， 听得懂吗？就是说啊，我们这边不讲90度，因为90度是人造的单位，但是2/π这种进度的单位，其实也是一个比例呀、啊。你可以想象2/π，不讲错了，2π是一圈嘛，那2/π就表示你走了1/4圈，这种也是一个叫什么比例的那种感觉。那当你讲到比例的话 ，strain 也是一种比例，所以你的 strain 跟你的 radian 是可以直接加在一起。OK 是直接通用的，所以你算出来一个 radian， 那其实就是它的 strain。OK， 所以你看到这边的2/π减 gamma，2/π加 gamma 就是它的 gamma 就是它的 shear strength。OK，next one sign convention really similar to convention just the law, the way we do it. Okay, don't ask me why. Because everyone use that. So now, shear stress, we need to give a definition for positive shear. Be careful, okay? You will have positive phase and positive direction because you see, you have a surface and direction, okay? So now I will give you the shear stress you see this element is at positive shear stress. All right. Now, why? How can we define it? You see, this area, we say positive phase. This area is positive phase. This area is positive phase. In contrast, by contrast, this one is negative phase. Why? Let's take a look. You can imagine that if you enlarge this volume, make it bigger, okay? This surface going to which direction? Positive x direction. If you enlarge this part volume, this surface going to positive y direction. But this surface, if you enlarge this, it go negative x direction. So this surface is negative surface, okay? And this surface is positive surface. Next one, if your stress, shear stress, acting on positive shear stress, positive surface, and then your direction going along positive y direction, plus times plus is positive. 正正等正. All right. But in the negative direction surface, you have the negative y stress direction. Negative times negative has positive. So this also belongs to positive shear stress. Okay, and you can examine another things. This one, positive y direction surface and positive x shear direction. Positive tells is positive. Okay, so you examine all these four. You can always get the positive convention. All right. So now I'm going to give you a bonus chance like that. Please go on the stage and plot a negative. Please give me a negative for me. Anyone? Go on the stage and draw it, please. Again, you only draw four surfaces, okay? Four surfaces. Excellent. Please write down, also write down your number, please. Number here. Yes. Thank you very much. This is thank you. I don't.
8.
8. Okay. So you can 8. All right. So you see that. Let's examine a little bit, right? This surface is positive x direction. Sorry, x surface, but the shear stress is along negative y. So positive times negative is negative, right? How about this one? This one is negative y direction, y surface, and this is a positive x direction. So positive, negative, negative. Okay, that's how we define the shear stress, positive or negative. Okay, and yeah, that's it. Ooh, difficult, right? Next one, hook law in shear. Luckily, even with the shear so difficult, concept is quite difficult, but the Hooke's law is still easy. Tension or compression, sigma equal to E times epsilon, E is Young's modulus or modulus of elasticity. Shearing is tau times equal to G times gamma. G is shear modulus. Again, we still talk about elastic. Okay, elastic. So, and the relationship between E and G is this one. And it's all related to Poisson ratio. Interesting. Okay, again, I'm not going to explain this in detail. I will explain this in the future. Okay, maybe next 2 weeks. All right. So just know that the E and G actually are correlated. Okay, has a relationship between each other. Okay, connected by new Poisson ratio. All right, I will tell you later. Next one, a very classic problem. Okay, let's take a look. So now you have a system. The system has a S called strut. Okay, the strut, if you see from here, this is the eyes. This is the eye. It's an eye. Okay, which means that you see through this angle and you will see this. All right. So you see through this. Okay, and you see this one. So the S is the squared tube. Okay. Strut is a square tube. Okay, and there is a pin. And connecting it with the gusset. I don't know what is gusset. G. Okay, so these two planes is G. Okay, and there are anchor bolts on it, 4 anchor bolts. Sorry, there's one behind the strut. Okay, 4 anchor bolt. What is anchor bolt? Anchor. What is anchor? Do you know? Anyone knows anchor? Wow, very good. So I just 锚船锚是吗 ？Very good. Copy. 哎啊，2次好了，这样子可以吗 ？Okay, very good. This is anchor. Anchor is look like this. So anyway, you know that you get the idea, right? Anchor. So anchor means that the anchor typically fix the ship or boat at that place. Otherwise, it will float with the sea, right? Float with the wave. So here is that these 4 anchor bolts make this stuff stay there. Okay. And yeah, that's it. And the base, this one. Okay, is a base. B. So now you can imagine that this, and then you can see the P is 54 kilonewton, and a lot of geometric parameter. Theta is 40 degree, D pin, TG, TB, D bolt, and it will ask you guess a sigma B between the strut and pin. All right, you see that the story is that your force is here, so the strut should be penetrating to the wall, to the ground, right? But something stop it. Well, which one is stop it? The pin, right? So this S, if there's no pin to stop it, this S will going out to the monitor straight to you. So you should think this pin, okay? So the pin bear that force. So sigma B is that you are going to see how much the sigma B is, how the pin bearing this force. So you can see that the S are going to hit you. But pin stop it. Where is the area stop it? Right? Two areas stop this strut to hit you. Okay? So what is the first strut? Sigma B is. So sigma B equal to, oh, another thing is that you have P and divide by and okay, and this is D pin. Okay, well, if okay, so what is the area of this red area at the red region? T times D pin, right? But you have two area, so either you said you time two, or you say each area has half of P. Both are okay because the stress, these two stress, bearing stress are the same. Okay, so either you say, oh, P area, P divided by T times D pin, but you have two area to bury, or you say each area subjected to half B. Okay, both are okay. Okay, so 54000 divided by 2, 0.012 times 0.018, 125 megapart. Okay, so thanks to the pin bear suffering this sigma bearing stress 125 megapascal to stop this S strong hit you, right? However, if this pin stop the S, the pin should go to you, right? Which thing stop it? Which thing stop it? Of course, right? So after the pin stop the strut, the pin still need to go into with go to you. So the G here will stop it. Will stop it. Okay, so this should be the problem 3. Okay, because the 3 asks sigma B between the pin and gusset. Okay, so sigma B equal to P divided by 2 T G times D pin. Okay, so sigma, the first one and third one actually are similar. Okay, Right, 0.015, 0.018 equal to 100 megapart. All right, so that's it. I will see you tomorrow. All right, we'll continue this example. And if you have any questions, come here. Thank you very much. Bye-bye.